conversion of second order reaction in non-ideal reactor. These were asked in 2022 as a 2-mark question in GATE chemical engineering. An elementary irreversible liquid phase reaction 2P giving rise to Q with a rate constant K, where the rate constant value is given liter per mole minute. Take place in an isothermal non-ideal reactor. The E curve in the tracer in the tracer experiment is shown in the figure. Pure P of the concentration 2 mole per liter is fed to the reactor using the segregated model. The percentage conversion of P at the exit of the reactor is how much? So we are directly given with the E curve, E of T versus T. It's a nice thing. You can split into a rectangle and a triangle. So by that way, you can easily deal this problem easily. So what is needed is the average conversion, which is average concentration 1 minus of Ca by Ca naught. Ca bar refers to average concentration. To get that, we need to know the Ca by Ca naught, what is happening in a batch reactor. That multiplied by the exit age distribution for the actual reactor, which is already given. So what is needed is we need to get the function of this. It is available in a graphical way. We need to get this in a functional form, or is E as a function of time has to be obtained. Then we can, and Ca by Ca naught will also be available as a function of time. That to multiplication, that integrated between 0 to infinity. Here actually we need to integrate between 0 to 0.5. There is a duration during which the material is spending in the reactor. The tracer is spending the reactor. Otherwise, a fluid element injected at time 0 will, the entire thing will come out at a time of 0.5. So that is a meaning of this E curve. So we need to integrate between 0 to 0.5. Okay. So for that, first thing is getting this equation for this line that is needed. What is the equation of that? For that, we don't know the value of this point, no? Because to get this equation, or is this this value is 0, 1, or is this point is known, whereas this point is, or is this point is 0.5, comma, the y value is not known. That value you have to get. But for that, we know the rule, that is the area under the E curve is simply equal to 1, or is the area of this portion is simply equal to 1. So this area you can get like this rectangle area plus this triangle area. So the rectangle area you can evaluate because this x-axis value is 0.5 and this y-axis is 1. So this rectangle area is available. And for this triangle, this rectangle area plus the triangle area should be equal to 1. So the rectangle area is available, which is coming as 0.5 into 1. That is 0.5 into 1. Sorry, this is the area. That is coming as 1 into 0.5, 0.5. So this triangle area is 0.5, which means we know this portion, that is the base, which is 0.5 minus 0, which is 0.5 is available. This portion is needed, so that we can easily evaluate. Because the area is 0.5 for the triangle, the area of the triangle is 0.5. So that is equal to, these points are known. So this point we are obtaining. So this point you can easily solve by equating this W is coming as 2, which means 3 minus 1. That is 1 plus 2 equal to 3. So W is equal to 2. Okay. That is this point value is now obtained, which is 3. So now we have this coordinates of this line 0, 1 and 0.5, 3. So for that we can simply get the equation, which is the equation of E is alpha T plus beta. So alpha you can easily get from this delta Y by, now delta Y is this value divided by delta X. So delta Y by delta X, which is a slope, which is nothing but the alpha, and intercept B you can obtain from substituting any of the value of E and the corresponding time. So from that we get this E as 4T plus 1. So E as a function of time is available. Now next thing is getting C as a function of time for the batch reactor. So for that we are given with the equation as 2P giving rise to Q, which is a second order reaction. For convenience, let us write it as A giving rise to B, because we used to write this rate as minus RA simply. So we are simply writing as 2A giving rise to B. This reaction is KCA square elementary reaction. So because of the stoichiometric coefficient 2, we have this rate order as 2. So K is equal to already given as 2 liter per mole minute. So using that, we are having this rate expression. And for the batch reactor, minus dCA by dt equal to minus RA. which is given as 2CA square. So you can integrate that and get the expression of CA by CA naught, which is of the form 1 by K CA naught T plus 1. So K value is already given as 2. So okay, otherwise also you can get this integration, which is CA by CA naught equal to 1 by 2 CA naught plus into T plus 1. So CA naught is also already given as 2 mole per liter. So using that, now we have this CA by CA naught simply available as a function of time. Already we know this E of t, which is also 4t plus 1. And this CA by CA naught is also coming as 1 by 4t plus 1. So in that case, simply cancelling out, simply CA by CA naught is simply 0 to infinity dt. So here it is 0 to 0.5 dt. So 0.5 is the value of the CA by CA naught. And whereas conversion is 1 minus of that, which is equal to 0.5. So the percentage conversion is 50%. So there is a accepted answer is simply 50%.